Okay, the topic of my talk today is synthetic data for big data privacy. I'm one of the founders of Mostly AI, and we are in this market now for 3.5 years and are preaching the advantages of AI-generated synthetic data for solving the big data anonymization dilemma for a while. And we are now in 2020 in a very interesting situation where already Gartner recognizes it as a huge opportunity, and they're starting to cover the market as well. And it's more and more understood the value that synthetic data can bring to organizations. This is my plan. I'm not sure whether I'm able to stick to this because I've prepared far too many slides. I will try to stay on time within the 30 minutes. And jump over to this one. This is a heavily oversimplified picture of the situation of privacy versus innovation within organizations. So on the one hand, we are sitting in this shiny, I think this is a BMW. We are collecting more and more personal data. We have plans to do machine learning and advanced analytics to develop smart services that are fueled by this immense stream of incoming new data and drive consumer understanding. And we really want to enable to get to this point to share data as much as we want to share as much data with as many people as possible. But on the other side, we also have an increase in privacy regulations that provide clear framework on under which circumstances, what type of data may be shared with which people and for how long. And plus there have been numerous privacy scandals over the past years where misuse of data was being uncovered and also covered by the press, resulting in negative reputational or in a bad reputation for the affected companies. And data protection is really then about sharing as little data with as few people as possible. And those are two forces that are on a continuous day battling against each other within the organizations. And it feels like we're sitting in this car and have everything in place, but we constantly pull the handbrake because we're not quite sure whether we're really allowed to do this or whether the public opinion will actually consent to our plans that we have with the data. Now, if privacy is such a big stumbling block, it begs the question, why don't we simply anonymize the data? Because anonymous data is not subject to privacy regulations anymore. That would be an easy solution. You simply anonymize the data, you're not subject to privacy, and you're unrestricted in how you process the data, how you share the data, and to whom you sell the data forward. Well, anonymization is hard. I did my best to anonymize this person, and I assume everyone on the line will be able to re-identify that individual, even though I masked part of the data set. I should have done better, and I should have masked more data. And I assume you would still have been able to re-identify that person, even though I pretty much destroyed already a third of the data. And even if you were not able to re-identify it, for a machine, this would be an easy exercise simply based on the lips or maybe by the shapes of the ears to re-identify that individual out of, let's say, 1 million other individuals. So in order to properly anonymize, I would have to go to this extent, and then I have successfully anonymized the data, but I have also successfully destroyed the utility of the data. So this is quite useless data. And it turns out it does not matter what type of anonymization technique, classic anonymization technique I apply to images, I end up with a very bad utility versus privacy trade-off. I can choose between having useful but not private data on the one hand, or to have private but useless data on the other hand. So the first row represents data masking, the middle row is noise injection or data perturbation, and the last row is generalization. And that is not only true for images, but this is true for any high-dimensional data asset. And the reason for that is we're all unique. We all have our own unique personal stories, are not like anyone else. And the more data points that are being collected about each and every one of us, the more unique we are within the data set. And the underlying law behind it is this curse of dimensionality, which means that the data space grows exponentially with the number of attributes, with the number of dimensions that are being captured. And this curse of dimensionality is kind of a challenge for doing analytics. It's a challenge for classic machine learning approaches. And it's particularly a challenge for protecting the privacy of individuals. Because in a highly dimensional data space, we tend to be in a very sparse data space and are easy to re-identify. To turn it positively, it's also a blessing for consumer-centric organizations, if you think about it, because if every one of us is different, an organization that is capable to cater towards these different needs and to serve and provide smart services that are tailored to individuals, there's really opportunity to provide to gain a competitive advantage. And one of the canonical case studies for anonymization is the Netflix competition that took place in 2006, where Netflix shared 100 million movie ratings for their subset of their user base. They did their best to anonymize the data and did not share any subject level information. They only shared these tuplets of user IDs, movie IDs, then the rating and the date. And plus, they also added some noise to this data to add some extra security layer to prevent re-identification. It turned out that it only took 16 days for two researchers from the University of Texas to partially de-anonymize the data set and to write a full paper on that, and also to run various to try to protect against their own de-anonymization attacks, and concluded that the amount of perturbation that would have been required to defeat their own algorithm would ultimately need to destroy their utility. And that's a basic law, and that boils down to, again, this curse of dimensionality. That was in 2006. Since then, and also before that, there were other academic studies and papers published, whether it is mobile trajectory data, whether it's financial transaction records, and even simple sociodemographic variables like date of birth, gender, and zip code are highly identifying variables. So it does not matter whether you consider a data attribute to be an identifier or a quasi-identifier. Pretty much any data point that you can link to an individual will serve you as a quasi-identifier, and in combination with other attributes will allow you to re-identify. What has changed over the past 2 years is that this has escaped kind of the academic research circles and made headlines in the mass media. So the New York Times is covering it, the Guardian is covering it, and the Harvard Business Review is covering it, and they go to the extent and they say there is no such thing as anonymous data. Which ultimately then results in this consequence, that the data assets are getting locked up. If you cannot safely anonymize big data assets, your default policy to access that type of data, whether it's for internal data sharing or external data sharing, will always be a healthy no. And that's then either the job of the chief information security officer or a data protection officer, who will need to ensure that the data is only used purposefully and lawfully. But how do you become data-driven, customer-centric if your customer data is being locked up? And that's the simple idea. So, and that's also what inspired us when we got started. That was research by NVIDIA showcasing the synthetic faces, fake faces of people that never existed but are shockingly realistic. And we thought, well, what is possible with unstructured data must also be possible to structured data, and that was also like my PhD background is on simulating behavioral data. So we also transferred then these methods and are now in the business of providing deep neural network models that are trained on actual privacy-sensitive structured data that allow you to generate an unlimited number of synthetic, statistical representative, and highly accurate, highly realistic data in unlimited volumes. And that is fully anonymous and can be shared and processed and utilized further without being restricted anymore. Now we are packaging this as a ready-made software solution that is being deployed within the organizations that runs either on-premise or in the private cloud. We will also have a SaaS, a hosted SaaS offering coming up in the third quarter of this year. There's also a public demo online on our website that you can access and try out. It's a limited version though, but you can upload publicly available data sets there, and with the click of a few buttons, we'll get a synthetic and statistical representative data set. Now, this is then our marketing slide, kind of like, okay, so while classic anonymization has this fixed capacity of how much information can be retained before you run into the re-identification risk, with AI-generated synthetic data, you break through out of that upper barrier. However, the key question is like, how good is that? So how accurate is that synthetic data? And that's actually an open challenge for unsupervised learning to find a single answer to this question, because there are multiple ways how you can measure the accuracy of a high-dimensional data set and compare to data sets. For one, you can do a simple Turing test and just challenge people to tell you, okay, can you actually discriminate between an actual and a synthetic data set? That's actually fairly easy to fool depending on the context. So while for images it's rather hard, for structured data it's fairly easy to fool humans. But it's really about retaining the statistics and the distributions at a broad level. So not just being able to generate the average customer, but to generate the full bandwidth, the full distribution, the full richness in behavioral patterns that are in the original data, then also in the synthetic data, and to provide a measure. And the measure that we are applying is the total variational distance for a range of correlations or univariate and bivariate correlations. Plus, there's another method, which is, of course, you can train your predictive models on top of the synthetic data, and you can benchmark the accuracy of a model that is trained on synthetic data with accuracy that is trained on an actual data, and see how much information you have lost. And my plan is now to talk through a couple of case studies that we have published also on our blog. And this is actually a data set that's also available in our demo where you can synthesize yourself then a data set. It represents US Census data. It's also quite commonly used data set in the synthetic data community, serves as a benchmark, and it has, the original data has 26,000 actual citizens with 15 attributes. You throw this into the generative deep neural network architecture, the patterns are being extracted, and then 100,000 new synthetic citizens are generated with 15 attributes, so it's structurally identical. The numbers are like, you will not find a single identical record from the original one. And the statistical patterns are being retained. And one way to look at this is by just plotting visualizations, and there will be now a couple of slides coming up which all follow the same pattern. In gray, there are the distributions of the original data set, and green is the result of running the same analysis on the synthetic data set. And while we see that the age distribution is near perfectly captured, the same applies for categorical variables as well as for binary variables. And it's not only about the median, but it's going to the full, I'm reporting here the the first percentile as well as the 99th percentile, these numbers all match. This is still actually rather easy. You could achieve this with simply shuffling your original data. What is more important is that you're retaining the multivariate relationships. So the relationship between marital status and age is quite apparent if you visualize it via a heat map. So people that have never been married are more likely to be rather young than older. On the other hand, people that are widowed are rather 50 years and older. And the same patterns will emerge whether you analyze the actual data versus when you analyze the synthetic data. And that applies to all the bivariate combinations. So we do this type of correlation plots, and we calculate for each univariate and bivariate correlation distance metric. As I said, this is the total variational distance, and report it then as a single metric, which is a way to look at the accuracy of synthetic data. It's by far not the only way, but it is inbuilt in the data synthesization process that there is this quality assurance report, and it's always being reported that this is the accuracy measure, a single number. The more data you feed into the training of the synthetic data generation, the higher the accuracy will be. And I mentioned that another test is to run a machine learning model on top of the synthetic data. And this is a setup that we have chosen here. So we actually split the original data into a holdout data set, 20%, and 80% training data. The synthetic data is generated based on the training data, so it was not exposed to the holdout data. And then there are the same machine learning model, and in this case it was a random forest model, is trained once on the training data, and then it's once trained on the synthetic data. And actually we did not do it just once, but we did it 100 times. And we evaluate the predictive accuracy for the target variable, for a target variable in this data set, and then benchmarked it. And this was a binary prediction task. It was predicting the income based on all the other variables. And what we plotted here, very importance on the right-hand side, the red dots are the true variable importance of a model trained on the original, and the green ones is the range of variable importance across the 100 generated synthetic data sets. But most importantly, you can see that the area under the curve as well as the accuracy only have a minor impact, and the conclusion is that you can train actually a machine learning model on top of the synthetic data, will get a near on par performance in terms of the predictive accuracy. But more importantly, you are able to do this on data that is fully private, that is fully anonymous, and so that exercise can be done by anyone, whether it's within your organization or outside your organization. Our focus is rather on behavioral data, and I've published, I think 2 weeks ago, an article on the importance of behavioral data and the challenges of behavioral data, because every event in a consumer record needs to be understood and analyzed in the context of the previous events. So whether a person visits your online website must be understood in the previous visit pattern, transaction patterns. Just like any word needs to be understood in the context of the previous words, or any musical notes needs to be understood in the context of the surrounding notes. So it's really about the sequential structure and the coherence of the data, and the question is whether the synthetic data is able to retain that. And for that, I'm now presenting another still simple data set on purchase history of actually a CD store back in 1997. They were active. And this is publicly available data. And every customer can have between 1 and I think up to 50 transactions. There's a transaction date, there's a number of CDs, a transaction amount being recorded, and the synthetic data engine will actually provide 50,000 synthetic customers in this case. And at an individual transaction level, again, the patterns match, but that's the easy part. Something that I would also want to highlight is that the derived measure, which is the transaction amount divided by the transaction CDs, which is the ratio between those two variables, is still also perfectly retained. But more importantly, it's the sequence. So the relationship between the attributes of the first purchase versus the second purchase. And of course, there's a high autocorrelation. People that tend to spend high on the first transactions are more likely to also spend high on their second purchase. And those patterns will reemerge, and they're, again, near identical whether they're analyzed on the synthetic versus the target. And then there is an endless list of ways how you can analyze sequential data. So you can look at the total transaction amount per customer, or the total number of transactions. You can look at the share of customers that had at least one transaction where they only purchased a single CD. And this is quite an interesting feature of the synthetic data engine, that it needs to first of all, it needs to be able to pick up the pattern, and then it needs to memorize while generating new data points that customer has had already a single CD purchase previously, so is then less likely to have another one. More statistics. This is the coefficient of variation, so it's a measure for the variance, normalized variance across the CDs and transaction times, and in particular also the intertransaction times. It's the time that elapses between two succeeding events, and all of them are perfectly retained. This is another example of then building a predictive model on top of the synthetic data and benchmarking it with the original data. One of the hardest challenges for us also over the past year was to synthesize mobility trajectories. We did now so for a publicly available dataset. It's the Porto taxi dataset. And you might wonder why taxi data would be privacy sensitive. It actually turns out the city of New York shared publicly the taxi rides, and there were de-anonymization attacks for celebrities who entered the taxi at a known time at a known location, and then were able to be traced back to their home location. Here, the data set is for Porto. We've also published our results on a blog post. And the synthetic samples, they follow the same, or they follow very similar patterns. This is only a small subsample now of the synthetically generated data points or trajectories. And again, no matter what type of statistics you are then applying on these trajectories, the results will match. So, and these are quite sophisticated measurements for the so-called straightness as well as for the radius of gyration that certainly the deep neural network was not aware of to consider, and still it's able to reproduce the same statistics in the to generate synthetic data that retains the statistical distributions. Oh yeah, here's the example. I actually inserted this where a celebrity entered the taxi and it was able to be traced back, even though the data set itself was supposedly anonymous, that was provided by the city of New York. This then brings me to the very important question, so how private is now the synthetic data? And there's an easy answer to say that, okay, synthetic data does not retain it does not have any one-to-one relationship, so you cannot re-identify any individual, so there's no risk. But that's not quite the truth, because of course you can build data generation mechanism, particularly an AI-based data generation mechanism. Without the safety measures in place, it will start memorizing individuals and it will be able to replay actual individuals. So you need to measure the impact of a single individual on the result. There's a whole framework around differential privacy, and there are ways how to build differentially private machine learning algorithms where you have a mathematical guarantee for the theoretical upper limit of the influence that a single individual can have on the outcome. Now, if you provide a synthetic data solution, however, you would need to gain access to the underlying algorithm as well as to the underlying implementation to be able to assess the correctness of that measure. So it's rather recommended that you actually judge the privacy by using the same algorithm multiple times and kind of calculate an empirical differential privacy. And plus, we recommend that you do a post-hoc analysis on top of the synthetic data, and that you will actually look at the distance between the synthetic data and the original data, because you really want that the synthetic data is as close as possible to the original data, but not too close. But what does it mean to be too close to the original data? Well, that can be answered by looking at the distance of an actual holdout data set. And the perfect synthetic data solution is one which generates new data that behaves exactly like actual data, but that has never been seen before. And then you have this magical solution of an infinite stream of realistic, statistical representative data that does not leak the individual level privacy of those individuals that were used as a training data. There will be an upcoming blog post also sharing some results by an external audit. So we as a synthetic data solution provider are continuously being audited also, so that our customers can have the safety of knowing that when they deploy our solution that this is truly non-re-identifiable and anonymous data. And it should be upcoming now in the next, hopefully, 1 or 2 weeks. This is already coming to the end. I hope I'm still within the targeted time. Use cases for synthetic data for privacy-preserving big data sharing. And we kind of see this in 3 buckets. For one, internal data consumers, where existing regulations and security measures prevent even the data to be shared internally. And we see this over and over again. This is actually the strongest demand, particularly for industries which have a long history of data protection, like the finance and the healthcare industry. For them, the GDPR did not change much of the situation. It's part of the DNA to protect the data. Actually, they now need to unlearn this and start embracing the data and the potential that is there in the data, particularly in the raw granular level transactional data. But for internal data sharing, it certainly serves the purpose of data governance. You can not only communicate on the meta level about data sets, but you can actually share realistic statistical representative samples that are strong indicators for what the data actually contains. We see many multinational organizations that are hampered by sharing data across borders by regulations. So it enables them to actually exchange the data at the granular level across borders, as well as across departments. And testing and development is certainly, it has always been the main driver for synthetic data, but with AI synthetic data, with AI generated synthetic data, the use cases for testing and development also go towards BI development as well as AI training. And as I've shown you, there is a loss in predictive accuracy, but it's minor compared to the fact that you're able to share the data in the first place at all. We say pull around embracing data literacy by educating internal staff about the available data, how to train machine learning, how to do analytics. And for that, you either turn towards publicly available data sets, which actually are quite boring, or you could turn towards synthetically rich representation of the actual data sets that are fully anonymous. Last but not least, it's data retention. This is kind of in sharing data with your future self, because you're not allowed by regulation to actually retain the data, but you're allowed to anonymize the data and then retain it. So maybe you right now don't know yet what our future use cases will be, so you are strongly advised to retain the data at the granular level and not aggregate the data, and still preserve it for later usage. There are then certainly use cases around external data sharing, whether it's research collaborations with universities or vendor validations. We work with the public sector, where they publish actually, or where they plan to publish and disseminate more data at the granular level. And then as the third block, we see more of an opportunity towards the future, really think about strategic partnerships among players in the market, where a financial institution could cooperate and collaborate with the telco operator and share at the very granular level their information that they are able to collect in a fully privacy preserved manner. And this is, I think this is my last slide, and like one more slide. This is again coming from our R&D department quite recently. It's a question: what's better than synthetic data? It's fair synthetic data. Where we did the exercise, we did not only train a generative model to with the target to be fully statistical representative, but also to have fulfill certain fairness constraints. And this US Census dataset that I previously talked about has a strong imbalance when it comes to the gender ratio and the income, the high income ratio across gender, where males have a far higher probability of ending up in the high income class. Now, any machine learning algorithm that will be trained on this type of raw data will retain this bias. Even if you drop the gender column, it will still be visible via the confounding variables. But we are capable of generating a fully synthetic yet fair data that accommodates, that counters this imbalance. So you end up with a near identical share of high income ratio across the genders, and all the other correlations are still being retained. So it is perfectly statistical representative data, with the exception that this imbalance between gender and income has been resolved. And yeah, I've come to the end of this this presentation, and very much looking forward to your questions. Thanks a lot.
All right. So thank you, Michael. So this was, I have always been a big fan of mostly AI. I think you're doing very one step ahead of everybody else.